NASA detected a mysterious object speeding toward Earth.
So on October 3rd, 3i Atlas will pass within 29 million kilometers.
A bright green stranger is rushing toward the inner solar system, and the calendar finally has ink on it. On October the 3rd, 2025, it skims Mars, then slings toward the Sun on October 29th. Telescopes see speed, light, and chemistry that refuse the rules, and every update tightens the same unsettling curve. If this is only our third interstellar visitor, why is it behaving like the first, with a plan? And what will we miss while it races through the glare? The first sighting, and the clock starts now. On July 1st, 2025, the Atlas survey in Chile flagged a faint mover sliding across a crowded star field at a pace that didn't belong to the Oort cloud or the Kuiper belt. Follow-ups from Hawaii, South Africa, and the Canaries snapped short arcs of light into a single hyperbolic path with an entry speed near 61 kilometers per second. Too fast to be born here, too straight to be captured. The designation 3I/Atlas arrived within hours, and with it the realization that we were back in rare territory. An object from another star system, the first since 2I/Borisov and only the third on record. Unlike its predecessors, though, this one arrived already loud. Even at several astronomical units, it was brighter than models allowed, showing a compact coma and a tail that refused the lazy geometry of sun-warmed snow. Amateurs noticed first during a blood-red lunar eclipse on September 7th. Images from Austria showed an icy blue haze. Hours later, Namibia recorded an emerald envelope, as if a switch had flipped while the moon crossed Earth's shadow. By dawn, the color held across continents. It wasn't a camera trick. It wasn't a calibration error. The green was real, persistent, and intense enough to be visible in modest rigs. Within days, the countdown crystallized. October 3rd would be the date of closest approach to Mars, a near miss by interplanetary standards at roughly 29 million kilometers, close enough for orbiters to try their luck. Then, 26 days later, perihelion, October the 29th, the day the object would plunge sunward into telescope exclusion zones and force Earth's best eyes to look away. The timeline framed everything that followed. Spectroscopists raced to book nights. Polarimetrists dusted off calibration lamps. Dynamicists spun up Monte Carlo banks to test every permutation of non-gravitational push. In Slack threads and midnight email chains, the same question surfaced after every plot and fit. If this is just a comet, why does it keep refusing comet math? If the schedule is set, what exactly are we meeting on those dates? And why has the color become the loudest clue? The community's mood swung between awe and unease because the cadence felt choreographed. Pre-discovery frames turned up in survey archives exactly where the refined orbits said they would, but each added frame only steepened the odds against chance alignments with the ecliptic and upcoming planetary geometry. Even seasoned observers who dislike drama admitted the calendar looked like a tour. A Mars pass timed for daylight geometry at the red planet, then a dash into solar glare right as Earth could have had its sharpest view. If the celestial schedule reads like an itinerary, what in the physics could be writing it? The green enigma. Green comets aren't new. Dicarbon fluoresces in sunlight and paints Comae emerald all the time. But when spectrographs locked onto 3I/Atlas, the expected swan bands refused to show. No C2 surge, no tidy explanation. Instead, the infrared blazed with carbon dioxide while water dribbled, an 8-to-1 reversal of the solar system norm that points to formation in a place colder and drier than the edges of our own planetary nursery. Trace CN and carbonyl sulfide appeared, but at levels too small to power the glare amateurs were recording night after night. Polarization measurements made the puzzle stranger. The way scattered sunlight rotated through the dust matched not inner-system comets, but the ultra-cold debris beyond Neptune, as if the grains were fluffier, older, and structured by chemistry that never spent time near a warm star. Then came the metal lines. Nickel, strong and repeated, while iron lines sulked near noise. Here, too, familiar pairings broke. In most comets, iron and nickel travel together. In Atlas, they separated like oil and water. One lab group floated a provocative mechanism. Volatile organo-nickel complexes, metal bound to carbon cages, could sublimate at low temperatures while iron stayed locked in refractory silicates. Under harsh ultraviolet light, those complexes would crack and radiate, leaving nickel fingerprints without iron's usual chorus. Whether or not that exact chemistry proves right, the inference is the same. The coma's brightness stems from processes and molecules that don't dominate in our backyard. Meanwhile, the green refused to fade. Through September, the hue stabilized, even as the comet brightened and the tail twisted under the solar wind, suggesting the source was not a transient flare, but a sustained, rotation-linked emission. Observers mapped periodic pulses against a spin period near 17 hours. Brightness peaked when the same longitudes faced the Sun, then slumped predictably. That regularity let dynamicists test whether the gas itself was nudging the orbit. Micro-thrusts from venting can fake small forces. The fits improved when timed jets were added to the model. It wasn't proof of intent. Nature vents too, but it did mean that the light and the motion were conversing. Take stock. An interstellar object with a hyperbolic sprint, a carbon dioxide-dominated chemistry, a nickel-heavy spectrum, dust that behaves like ancient trans-Neptunian fluff, and a green color without the molecule that normally makes green. Stacked together, these lines of evidence stop feeling like footnotes and start sounding like a thesis. If the color points to unusual chemistry, what does the path through the solar system whisper about purpose and timing? And if a light curve can double as a steering log, even subtly, the arrival windows ahead, Mars, then perihelion, shift from passive appointments to tests of how emission and trajectory dance together under sunlight. Windows we get, and windows we lose. Interstellar visitors should cut through the solar system at odd angles, miss the planets by insultingly wide margins, and leave before we can say spectroscopy. Atlas threaded the ecliptic within a few degrees, a highway merge rather than a plunge from above. Monte Carlo clouds built from thousands of synthetic clones converged on the same choreography. Mars, on October the 3rd, at roughly 29 million kilometers, then a brush with the Sun on October 29th, and a long, cold exit. The odds of that planet-skimming sequence by chance stayed low even as uncertainties tightened, which is why dynamical modelers kept asking the impolite question, are we seeing selection bias, or a path that was, in some sense, selected? Intent isn't a parameter you can fit, but you can map opportunities. Closest approach to Mars arrives when the red planet has assets in place, the Mars Reconnaissance Orbiter with HiRISE for high-contrast imaging, MAVEN sniffing the upper atmosphere, and ESA's Trace Gas Orbiter capable of sensitive spectroscopy. From Earth, by contrast, our flagships face geometry that reads like a lockout notice. Neither Hubble nor JWST can stare toward the Sun's neighborhood during the critical weeks around perihelion. Their safety cones are strict, their pointing rules uncompromising. Ground-based giants will fight twilight and low solar elongations with heat-shimmering air. That imbalance matters. If you wanted to reveal chemistry to instruments that can pass it and hide your nucleus from the eyes that might resolve it, you could hardly choose better dates. To be clear, celestial mechanics can produce accidents that look like plans, but what matters for science is exploiting the accident. Teams at JPL and Goddard drafted rapid observation campaigns, Mars as the forward outpost, Earth as the rear guard, heliophysics spacecraft watching the coma's interaction with the solar wind. Every plan is a hedge against loss, because once Atlas dives into glare, will wait on Mars for images and spectra that would otherwise be ours. If HiRISE resolves a point source where a fluffy nucleus should be, theories will fall like dominoes. If MAVEN and TGO see carbon dioxide jets strobe with the spin phase, non-gravitational forces will graduate from suspicion to measurement. If neither happens, the mystery simply changes costumes. A natural object with alien chemistry is still a prize. While the path ties our hands around the sun, the coma keeps talking, so what exactly is it saying about the world that made it? Chemistry from another sun. The 8:1 carbon dioxide to water ratio is a blunt instrument, but it points in a clean direction. Atlas formed cold. Colder than the water frost line around a sun-like star, cold enough that carbon dioxide and even stranger volatiles could condense, sheltering organics and metal complexes that shatter under warmer rules. In that deep freeze, dust grows differently. You don't bake silicates and carbon into tight pebbles. You knit ultraporous aggregates with icy cements, fragile as ash, and yet tenacious enough to carry memory for billions of years. Polarization curves echo that structure. The way the coma flips the plane of light tells us the grains are fluffy, irregular, and likely coated with materials most comets shed early in their lives here. That is why every nickel line matters. In our neighborhood, nickel and iron are twins. In Atlas, nickel sings solo. One plausible path is organo-nickel chemistry, the kind of stuff bench chemists coax in flasks, but space can assemble given carbon, time, and ultraviolet light. Bind nickel into cages that sublime shy of iron's threshold, and you've created a spectral lever. Nickel in the gas phase, iron in stubborn rock. Even if a different molecule ends up guilty, the verdict won't change. We're watching unfamiliar feedstock evaporate. The green, divorced from dicarbon, forces a parallel thought. If C2 isn't the painter, what is? Candidates multiply, metastable radicals, photofragments of carbonyl sulfide, exotic carbon chains that glow at the right wavelengths when hammered by sunlight. A lab can chase them, but the coma is the only reactor built at interstellar scale. Then there's the cadence. Emission pulses locked to a roughly 17-hour rotation invite a simple, dangerous inference. Vents. Natural vents, surely, but vents that act like valves. Turn toward the sun, pressure rises, gas escapes through the path of least resistance, the coma brightens, the non-gravitational term in the orbit fit tilts ever so slightly, and a day later the cycle repeats. Stack those kicks for months, and you tweak a flyby distance by thousands of kilometers. That is not a conspiracy. It's physics with consequences. Planetary scientists have walked this road with comets before, but they walked it with water in charge. Here, carbon dioxide leads, and carbon dioxide pushes harder per molecule. That is why the arrival windows matter so much. If Mars sees the strobe, we'll measure thrust. If Mars sees a smooth glow, we'll downgrade intent and upgrade alien geology. Either way, the chemistry isn't a curiosity. It's the engine of the mystery. Engines, even natural ones, leave wakes. So what has the wake already changed about what we can and cannot observe from Earth? And if chemistry steers, strategy follows, because analysis must chase the forces that matter most. How we watch, when we can't look. Every flagship telescope has a keep-out zone around the sun, and Atlas is about to camp inside it. Hubble's sun angle limits and JWST's even stricter pointing rules turn late October into a hard blackout for the very instruments that could resolve a nucleus or dissect faint spectral lines in the deep infrared. Ground observatories can push closer, but low elongations mean short twilight windows, atmospheric turbulence, and brutal background light, which is why mission planners pivoted to Mars. On October 3rd, Mars becomes our forward operating base. HiRISE, built to read license plates on the Martian surface from orbit, cannot literally image the nucleus at interplanetary range, but it can hunt for unresolved point sources, jets, or high-contrast structures against the coma. MAVEN and the Trace Gas Orbiter bring spectrometers tuned to sniff tenuous atmospheres. Repurposed, they can watch Atlas's gas ratios evolve hour by hour as rotation swings active longitudes into sunlight. Even if signal-to-noise is mean, stacking thousands of frames can tease out periodicities and line strengths we'll never get from Earth that week. Meanwhile, heliophysics assets, solar orbiter, stereo survivors, and a flotilla of monitors will watch the solar wind sculpt the tail, turning plasma physics into a proxy for unseen geometry. This patchwork is not elegant, but it is honest. Astronomy often advances by turning constraints into instruments. Past that window, Atlas races sunward, and we live with the silence. That enforced pause is a test of discipline. It tempts overinterpretation of partial data and amplifies the narratives we bring to the sky. Some will argue for an engineered visitor taking tactical advantage of our blind cone. Others will point out that celestial mechanics deals everyone a weird hand eventually, and that we remember the weird hands that flatter our hunches. The only remedy is more measurement. Happily, the era of chance is ending. Vera Rubin's all-sky cadence will catch the next interstellar in its first act. Rapid response probe concepts, solar sail couriers, modular flyby cubes, even swarms, are maturing from white papers into hardware roadmaps, built to launch inside a year and meet a target on its way in, rather than waving at its tail. Atlas, for all its timing, is sharpening that case. It exposes the seams in our coverage and the choices we'll have to make when the next alien chemistry set crosses the border. And when the measurements land, especially from Mars, what story will they tell about risk, readiness, and the kind of universe we've actually been living in? The sober answer may be neither nightmare nor comfort, but a recalibration. Interstellar visitors are rarer than comets, yet common enough to plan for, and different enough to force upgrades in how we defend and how we wonder. What Atlas changes now? Every civilization meets a mirror from the sky. Copernicus turned Earth into a planet. The Apollo photographs turned it into a home. Interstellar objects do something subtler. They turn our solar system into one sample among many. Atlas underscores that lesson with chemistry that doesn't obey our defaults and geometry that squeezes our coverage at the exact moments we crave clarity. It is not an omen. It is an audit. What do we learn from the audit? First, that planetary defense remains pointed at the wrong gaps. We have excellent schemes for cataloguing near-Earth asteroids in familiar orbits, but a fast, hyperbolic visitor from a low elongation angle exposes blind spots that a single constellation of infrared scouts and a modest expansion of radar and space-based parallax could close. Second, that laboratory astrochemistry must widen its menu. If organo-nickel complexes, odd sulfur carriers, or long carbon chains are plausible coma engines, we need spectra, cross-sections, and degradation pathways measured under UV fields and temperatures that mimic alien outskirts, not just the comets we grew up with. Third, that rapid response missions are no longer luxuries. A shoebox probe with a telescope and a mass spectrometer, solar sailed into a crossing trajectory, would answer in a week what the best remote assets dither over for months. Fourth, that public expectations need careful shepherding. The internet now watches discovery in real time, where gaps become conspiracies and cautious language sounds like evasion. Clarity about what we know, what we guess, and what a single plot can or cannot say is part of the scientific job. And finally, that wonder remains a working tool. Curiosity funds telescopes, trains analysts, and keeps amateurs awake under cold skies where the first hints often appear. Atlas has already paid that dividend. Kids who learned the word hyperbolic this summer will be coding survey pipelines a decade from now. So where does the story likely go next? If Mars returns time-tagged spectra with carbon dioxide surges tied to a 17-hour spin, we will bind non-gravitational forces to measured vents and call the steering subtle but natural. If HiRISE sees unresolved structure or jet asymmetries that refuse comet logic, debates will sharpen and proposals will multiply. If, against odds, we glimpse the nucleus and find it small, dense, and oddly reflective, a few wilder branches on the decision tree will gain weight, and we will write careful papers that say as much without claiming too much. But even the most conservative outcome leaves a revolution intact. A comet whose green glow isn't dicarbon, whose metals split their usual duet, and whose dust scatters light like relics from beyond Neptune. Forces textbooks to add new chapters. Transitional hook, which leaves one last piece, the part where you and I decide what to watch for as the calendar turns and Atlas keeps its dates. What this visitor demands from us, now 3i/Atlas, has already changed the questions we ask, and in a few short weeks it will change the answers too. Its schedule: Mars on October the 3rd, perihelion on October the 29th, turns our blind spots into experiments, forcing us to rely on Mars-orbiting cameras and spectrometers while Earth's flagships look away. Its chemistry: carbon dioxide in command, nickel singing without iron, green without dicarbon, tells us formation stories from a colder, older frontier. Its pulses and possible micro-thrusts remind us that physics can imitate intent long before intent is proven. So what do? We measure through the glare, coordinate amateurs with missions, harden archives for faster recovery, and fund rapid probes that can be ready before the next hyperbolic track appears. We expand the lab menu to include organometallics and exotic radicals, and we tell the public exactly what the data say and what they do not. Whether Atlas is only alien geology or something designed, it narrows our ignorance either way. Wonder is not a weakness, it is an instrument. Keep watching the calendar, keep asking better questions, and we will meet the next messenger with sharper tools and fewer excuses. Until then, mark the sky and stay ready for the truly unexpected ahead. Atlas will pass Mars on October the 3rd and dive toward the Sun on October 29th. If you want the Mars images decoded, the spectra translated, and the big questions sorted from the loud guesses, subscribe, share this with the one friend who always looks up, and tell me what you want answered first. Starting tonight, right here with us live.